All right, guys, good morning. We are going to be back at it. Well, that was unpleasant. Oh, you guys get a little comedy to start yourselves off. What questions do you guys have for me? Because effectively this week is your review for exam one. You guys have questions, go ahead and put that in the chat, or you guys can go ahead and ask it. Hello? Sounds good. Okay. So when we're talking about a torque question, is there anything in specific you want to go into? You guys can hear me, right? You guys can also go through and unmute yourself so we can hear you. Okay. Practice questions. Make that, I'm going to mute you guys again so that way we're not repeating back my own sound to me. Okay, so I've got the review questions also up, so let's pull those up. And let's go ahead and come on down. Okay. So now we're talking about torque is in balance, because here's an easy torque question, well, relatively speaking. Okay, so how much force has to be produced if a lever has a resistance arm of 0.75 meters, a resistance of 20 kilograms, a force arm of 0.03 meters? So effectively, we've got one side and the other side of the lever with the fulcrum in the middle. So we're going to go ahead and let's say we're going to try and draw it up behind me. Okay. See if I can make this a little bit bigger. Bring that down a little bit. So you see things a little bit more. Okay. So if I'm drawing this across, okay, we've got our fulcrum because the one side is simply 0.03 meters. The other side is going to be pulling down at 0.75 meters. We're saying the fulcrum doesn't weigh anything. And then over here, we've got a 20 kilogram weight at the end. Okay? kg. Now, we need to figure out then, what does the force have to be over here in order to keep this in balance? So we know that resistance times the resistance arm equals the force times the force arm. So we've got our resistance, we need to convert this into newtons. So we take 20 kilograms, okay, multiply that by 9.81. So now we're into newtons, multiplying that by 0.75 meters equals the force, which we don't know, times the force arm, which in this case is 0.03 meters. So we're going to divide both sides by 0.03. So these cancel. So we have force equals 20 times 9.81 times 0.75 divided by 0.03. Does that make sense, guys? Go ahead and say anything over chat. Thank you, Blaine. Thank you. Yeah, just say anything over chat if you guys have questions. Otherwise, if it looks like the board's going to hit me in the back of the head again, please give me like a heads up or say something. I'd appreciate that. Okay, so what other questions you guys want to go ahead and try to break down some? This has been a very riveting review so far. Okay. So let's go ahead. Yes. Okay. So Haley, give me one moment. It's going to be uh, 4905 is what I came up with. What other questions you guys want to go through? Ooh, great question. Okay, so when we're talking about compression, and this is actually this is kind of a fun one if we're going to talk about biomechanically speaking and how much the spine's actually going to be encountering. Give me one moment, I'll grab something to erase all this. Okay. All right. So if we're going to have somebody squatting, okay, so we've got somebody standing with the bar, okay, if it's the back squat, the center of mass can be behind the body. If it's overhead, the back mass can be on top of the body. If it's front squat, the mass is going to be slightly in front of the body. Okay. Now, the biggest key with the greater amount of compression is going to come down to the greatest amount of load. So whichever squat you can lift the most is going to have the greatest amount of weight that you're having to tolerate. Now, what's interesting about this load that we're having going through the compression, okay? Once again, that's just the force going down. Hey, what's up, Tinks? You doing good, girl? Okay. Now, the bigger key that we're looking for is probably the greater amount of shear. And shear, remember, guys, is going to be the force that's going to be pulling us forward. And it turns out the front squat is going to help us stay in the most upright position. So relative forces, we're probably going to be experiencing a greater amount of compression and less shearing. Overhead squat, because we naturally are not going to be able to overhead squat as much as we can front squat, much less as much as we can back squat. We're going to have even less compression and less shearing. But the back squat, due to the bar being behind us, and for you having to effectively have a steeper body angle in the bottom because of this load behind you, you're going to find that this is going to cause the greater amount of shearing force in the spine as they're going down. Does that make sense? what are the questions you guys want to go over? We can just work on more from the review if you guys want. Doesn't bother me any. You guys can unmute yourself if you guys want to ask a question that way, or you guys can just go ahead and send it over to the chat. Possibly for the centripetal force. The key is if we come over and give me one moment. Just remember, guys, like anything else, we're just running the formulas. So when we're talking about centripetal and centrifugal force, it's all we got to run. The mass multiplied by the radius and by the degrees per second, or the actual technical linear velocity you have. Oh, nice. So we're going for the one from the review. I like it, Lewis. Okay, so Lewis is wanting us to go ahead and take a look at this guy. Now, we're trying to figure out the lifting force that bicep has to produce. Okay, so we're going to once again bring ourselves back to having the arm that's parallel to the ground. Okay, and then we do know it's going to be pulling upwards in what is going to be here an 86-degree angle. Okay, now the weight is going to be 25 centimeters down and weighs a grand total of 20 kilograms. Okay, the arm center of mass is going to be half of this, so it's going to be right here, and that's going to be at 12.5 centimeters, and it's going to weigh a grand total of 5 kilograms. And so the bicep itself is attaching right here at only 2.5 centimeters. So we have our force, which we need to solve for, times 2.5 equals 5 times 9.81, so we can convert into newtons, multiplied by 12.5 plus, because that's just the arm, 20 times 9.81 times 25. Okay? So this is going to go ahead and give us a grand total. Oh, I'm sorry. So now we'll divide both sides by 2.5. So those cancel. So our force, and we're still going to have to do our trig, but we still got to solve at least for that initial force. So that's going to give us a grand total of 20 times, oh, yeah, using the calculator on my computer, so I didn't have the correct output set up. That's funny. Times 9.81 times 25. Enter. Okay, which gives us, for this part right here, 4905. Okay, so now we're going to go ahead and take 5 times 12.5 times 9.81, which gives us 613.125. So now we're going to add those two together because we need to make sure we're always following our order of operations. Then we're going to divide that by 2.5, which now our initial F is going to be equal to 2,200 and 7.25. So since we're trying to figure out just, right now we only have the vertical component here, okay? So we want to solve for the hypotenuse. Which of our different trig functions do we need to use? Okay, so remember, cosine equals what? SOHCAHTOA. So right now, the way this angle's set up, this right here is the hypotenuse, this right here is the opposite, and this right here is the adjacent. So we actually need to do the sine, the negative first, of 86 degrees currently equals 2207.25 over the hypotenuse. So we'll move each to either side, and we'll take 2207.25 divided by the sine of 86 to the negative first. So that comes up to 0.997 56. Let's just go for it. So then we're going to go ahead and take 2207.25 divided by 0.997564. It's going to equal, altogether, once we factor this through, our final actual bicep force equals 2,212.63. Now you could round up to 6.4 because it's actually 6,399. Sorry, duck out of the way so you guys can actually see that. What other questions do you guys want to go ahead and work your way through? Sounds good, Colleen. Okay. Okay, sounds good. We'll go through both of them. Okay. So first, to start off with the strain, notice right here, what is the total amount of strain that an object experiences if it compresses 20%? So the idea is, you're talking about, think of a spring. So if it goes from 0 to compressing 20%, and it requires 500 newtons to compress it 5% in a linear organization, meaning when we're effectively at 0 degrees, or sorry, 0% of compression, we're using 0 force, okay? So now, (5%) equals 500 newtons. So then 20% equals how many newtons? Think of it like a graph. We're at 0, then at 5%, we're at 500. So when we get to 2000, we're going to be at 20% because it's just going to keep following that same linear relationship. Greetings. I know, you never get enough attention from me. I'm sorry, I'm trying to teach. I'd be very happy if you didn't knock over. Oh, she just knocked. Display. This is going to be, hey guys. This just got weird. Okay, thanks. Kitty on the floor. All right. Well, that was my cat, and she literally just knocked out the stuff we had there. Okay, so first we're going to go ahead and go through the torque required question. So let's go back to sharing screens. Okay. So now if we're looking for the torque required whenever we're trying to do some rotation, right here is what we're looking for, Colleen. So we can either have the inertia multiplied by the acceleration, or we can take the mass. You gotta go back on the floor. Okay. I know. I'm so mean. I'm just trying to, oh my God. Okay, so if we have our inertia, we have our mass times the radius, then we're going to go ahead and be able to effectively show or be able to see relatively easily how much torque is going to be required. Okay? Sorry, the cat kind of just knocked out. Oh my God, you're such a... This is the brat, this right here. Colleen, I apologize, Catherine, that the board is hard to read. I will try to get that closer so you guys can see that. Colleen, does that answer your question about effectively how we look at the torque and how you figure out what the amount required is?
Yes.
Okay, thank you. Okay, how fast do you have to jump off the ground in order to jump at least 2 meters in the air? Okay, so this one is going to be simply the kinetic energy equals our potential energy. So in this case, let's go ahead. I did not like getting hit in the head by this board earlier, so I'm just going to pull this thing up closer so you guys can see it a bit better. Now, let's go ahead, scoot you back a little bit. Let's have you here for now. Okay, So in this case, potential energy is going to equal our kinetic energy. What this means is mass times gravity times height equals 1/2 of the mass times the velocity squared. So when we ask ourselves how fast would we have to jump off the ground, well, what that effectively means, you guys see that a little bit better, okay? What this means here is that what we're going to do is immediately we can go ahead and get rid of the masses, because it turns out it's the same mass both times. Now, gravity, since we're doing this on Earth, is going to be 9.81. And scoot this over so I can try and write right-handed so you guys can laugh at my great penmanship. So you're going to take 9.81, can you tell I'm left-handed, multiplied by the height, which is going to be 2, equals now 1/2 of our velocity squared. So now we're going to multiply both sides by 2. So that way, 1/2 times 2 equals 1. So now we've got velocity squared equals 2 times 9.81 times 2. So now we're going to go ahead and take the square root of both of these. So square root of something squared, 0. So we have 2 times 9.81 times 2, and the square root of that is going to equal our velocity to jump off the ground. Does that make sense, guys? Okay. What are the questions you guys want to go and work your way through? And of course, now I can't see the chat. Oh, there we go. Fifth one on the review about the apex. Okay, yeah, sounds good. So this is actually just like what we just did, where at the apex of flight, 10-kilogram medicine ball is 3 meters off the ground, so hence it can fall 3 meters, and has a horizontal velocity of 10 meters per second. It's the total amount of energy this object has. Well, right now, because this object is flying through the air, okay, it has both kinetic energy because it's going forward, and it has potential energy because it can fall downwards. So you have to use both of them, which means we're going to have, well, kinetic energy, which is it's a 10 kilogram ball times 10 meters per second, which will be squared, and we take 1/2 of that. So 10 times 10 is 100. 10 times 0.5 is 5. 100 times 5 equals, it has a kinetic energy of 500. Now we have the mass, which is 10 kilograms, multiplied by its height, which is going to be 3 meters, and then multiplied by gravity, which is going to be 9.81. So then we have 30 times 9.81, which is going to give us, morning, Bahamut, how you doing, bud? So let's go ahead. We'll take 30 times 9.1, which is going to give us 294.3. So now we're going to go ahead and add both of these together. So we end up with 794.3 for our total amount of energy. How did I get 30? Potential energy equals mass times gravitational pull times height. So hence, mass is 10 kilograms, height was 3 meters. So that's 30 times 9.81. What are the questions you guys want to talk your way through? Yeah, I know what you're talking about, Blaine. I'm just going to try to get it closer to you guys so you can see it from there. Seeing as a whiteboard? Oh, this is because it's going to make it here. What are the questions you guys have? Well, if you guys don't have any more questions, I just put the video up for the vertical jump lab on YouTube yesterday, so you guys have got that. You'll be able to see all the numbers you need in order to figure out your math there to submit that. Don't worry, I'll push back lab 3's due date, so everybody will be okay. All the other videos for all the other labs are up online. You've got everything you need on them. You just have to watch the videos and see the numbers that come up, write them down, do your calculations, and you'll be good to go. As for your projects, make sure you're still talking with your classmates about how you guys are divvying up the work. I know it's going to be really hard to video the movements now. Just do your best given the confines of what we're dealing with. And then the other side of it being for the exam, I'm going to go ahead and have that open on effectively Thursday. And it's going to be open from Thursday afternoon until probably Sunday night. Or actually, you know what, we'll go the individual one that's open from Thursday until what'll probably be Friday evening or Saturday morning. And then the group exam will open from Saturday until pretty much Tuesday before class. So that way you guys can figure out a time to get online with whomever you want to go ahead and take the group exam with. With the group exam, you only have to have one person in the group take the exam. Everybody else, the grade's just going to copy over, so you don't have to worry about having to go ahead and each person do the exam. And outside of that, yeah, any questions, comments, concerns, anything else that would help you guys with reviewing for the exam? Sure, I can send out an email if need be. So if you guys don't have any other questions, I'll give you guys a couple more seconds. You guys can unmute yourself and ask it out loud, and from there we'll go ahead and, yeah, call it a morning. Is there chapter 7 quiz due this morning? Good question. I believe it's the one that was effectively, you should have taken it last week, and it's going to be open all the way through, I think it was today, or is today, for the chapter 7. Give me 1 second, I'll pull it up on my other screen. And it looks like I've got you guys, so you've got plenty of time on it, but let me double check. Yeah, they're all still open. The Hall 7 quiz and then the Chapter 9 quiz. Thank you, Lewis. Yeah, so you guys got time. I know a lot of you guys are kind of scrambling, and you guys are the ones that managed to make it to lecture, which means there's a lot of other folks that who knows what's going on. And let's see here. Currently, there's 16 people here, and there's almost 30 people in the class, so that does not bode well for everybody's had the chance to get online and be able to get all this stuff moving like they need to. So, any other questions or anything else you guys want to go ahead and talk about? Hope you guys are doing okay. Yes, I'm going to save it, and then I'm going to put it all up on YouTube again. All these lectures, all these reviews, anything that I record with you guys, I'm just saving it and just putting it up on YouTube. Whenever you look under the Biomechanics tab, where it's got like your lab videos, I've got these up there. I don't know, I'm a little worried that somebody might get butthurt about copyright, so that's why I'm having them unlisted. But you'll be able to see them whenever you click on the tab. So, all right, guys, stay safe out there. Hope you're doing okay with everything. This sucks, but we're going to try to make our best with it we can. And yeah, if you need anything, you guys know how to get a hold of me. Okay? So be safe and bye-bye.